Good morning. On behalf of the ESCO Group, I would like to welcome all of you to today's webinar. Your presenters today will be Randy P.T., Vice President of Program Development, and that's me, then Eugene Silverstein, Director of Technical Educational Standards. He'll be covering Type 2 this morning. Before we get started, we want to inform everyone of our webinar format. To be respectful of everyone's time, we will end our presentation before an hour is up. All attendees will be muted throughout the presentations. You may submit questions through the question toolbar on your control panel or by sending a message through the chat feature. If time allows, we will answer as many questions as possible at the end of the presentation. If we're unable to get to your question, we'll follow it up with you by email. Also, this webinar will be recording, and the recording will be available in the Proctor login area of the ESCO Group website. This is the fourth in the series of webinars intended to help the ESCO proctors prepare students and technicians for the EPA Section 608 exam. Today, as I said earlier, we're covering Type 2. Next week, we'll be covering Type 3. All the times for these webinars are in the Central Time Zone, and you must sign up for each webinar. At this time, I'd love to turn the webinar over to my esteemed colleague, Eugene Silverstein.
Thanks, Randy, and good morning, everybody. And again, thanks for attending. This webinar is based on the PowerPoint presentation that's available to registered ESCO proctors. The information contained in the PowerPoint is intended to help prepare technicians and students for the EPA Section 608 certification exam. It's important that you let your students know that the slideshow you present to them is meant to serve as a guide for reviewing the material related to Section 608 of the Clean Air Act. It's not intended to replace a formal refrigeration training course, although this prep course may very well be part of your training course. In essence, someone who's preparing for this exam should be familiar with the basic vapor compression refrigeration cycle, common service equipment practices, and procedures. It's also important that your students are aware that although the training they receive reflects the most common information available at the time the content was created, regulations and guidelines do change periodically. So if the EPA regulations change after an individual becomes certified, it's their responsibility to be aware of and comply with these changes. It's also important to note that the EPA reserves the right to modify the test questions and or require new certification or recertification based on advances in technology. As a registered proctor with ESCO, you have access to all EPA updates, and all you have to do to view them is log into your proctor account. The ESCO Institute will update the training manual and PowerPoint presentations as necessary to reflect the current EPA regulations, guidelines, and testing requirements. So if you're ready, and even if you're not, let's take a look at Type 2 section of the 608 certification exam. A lot of the material that we're going to be looking at right now should not be new to you, especially if you've been training your students for some time before, but there are some significant changes to the regs, and I'll be pointing those out to you as we make our way through. So Type 2 certification is required for technicians who will be maintaining, servicing, repairing, or diagnosing medium, high, or very high pressure appliances. The exception to this rule is those individuals who service small appliances and motor vehicle air conditioning systems. Of course, for those individuals who possess universal certification, they're good to go as Type 2 is rolled into that technician certification. Although this has been mentioned in previous webinars, I just want to reiterate that as you work through the presentation with your students, pay special attention to the important text that is color-coded in red. In our previous webinar on type 1, our colleague Len Palmer gave out some dynamite suggestions on how to use this content to help prepare your students for that and for preparing for the exam. So the techniques that he outlined last week can definitely be utilized with any of the content for core type 1, type 2, or type 3 to help prepare your students. Your students will need to know the definitions of various system classifications, namely comfort cooling, commercial refrigeration, and industrial process refrigeration, or IPR. Comfort cooling applies to appliances that supply cooling in order to control the heat and or humidity in occupied spaces. Residential, office, and commercial buildings are all examples of applications that are included in this category. The commercial refrigeration category includes equipment that is used to preserve products, as in the retail, food, and cold storage warehouse sectors. The industrial process refrigeration, or IPR category, includes equipment that is used in a number of industrial processes, including those that are listed here. Some appliances are used for multiple purposes and will fall into more than one of these three categories that were just outlined. These systems are referred to as dual-use systems. When an appliance has multiple uses, its classification is determined by the highest use percentage. So if 55% of a system's capacity is used to provide process refrigeration for its manufacturing lines, and 45% of its capacity is used to air condition the office spaces, this system would be classified as an industrial process refrigeration system because the IPR aspect of the system is taking up more than 50% of the system's capacity. This is important because the allowable leak rates are different for the three different system classifications. So now that we know how the systems are classified, the total system charge must also be known in order to determine if the amount of refrigerant that is leaked from a system is below the new limits. If the appliance is a package system, use the charge indicated on the equipment nameplate to calculate the unit's leak rate. The refrigerant charge for split systems can be determined by using the factory charge as the base and then adding to it any additional refrigerant that is required to compensate for refrigerant lines and piping accessories. The system's annual leak rate is easily calculated by dividing the total amount of refrigerant added to the system over the past 12 months by the system's total charge. With this, the leak rate will be expressed in decimal form. Multiplying this result by 100 will give the annual leak rate expressed as a percentage. So, for example, if 125 pounds of refrigerant is added to a type 2 appliance that has a total charge of 500 pounds, the annual leak rate is 0.25 or 25%. Now, it should be noted that the total amount of refrigerant is ideally the amount of refrigerant added over a 12-month period, but you don't have to wait 12 months to calculate that. So, for example, if a system is repaired at the beginning of February and a technician adds 100 pounds of refrigerant to that system, and then at the end of March, an additional 100 pounds of refrigerant has to be added to that system, we added 100 pounds of refrigerant over 2 months. So by extrapolating, that would actually come out to be a leak rate of 100 pounds of refrigerant every 2 months for 1 year, giving us 600 pounds. So that can actually be extrapolated out as well. Now, depending on the total charge of the system, then we can determine the actual percentage of the leak rate. So a unit's nameplate provides a great deal of information about the system. So make certain you teach your students how to read these system labels and extract information from them. For example, Inspecting the unit's nameplate is the easiest way to determine the refrigerant that's used in a packaged rooftop unit. In addition, as we mentioned before, the unit's nameplate also indicates the package unit's total charge. Knowing the system's total refrigerant charge also makes system charging easier. When the system's charge is known, it's always best to charge the system by weight. Of course, liquid charging through the liquid line service valve is much faster than vapor charging, especially when the system holds a lot of refrigerant. One thing I like to do is ask my students which method of charging is faster, liquid or vapor, and that just helps to stimulate some classroom discussion as you work your way through this content. The maximum allowable leak rates have changed effective January 1, 2019. The old 15% and 35% leak rates are gone. The new leak rates are based on the system classification. So for comfort cooling equipment, the maximum allowable annual leak rate is 10% of the system charge. For commercial refrigeration equipment, the maximum annual leak rate is 20% of the system charge. And for industrial process refrigeration systems, or IPR, the maximum allowable annual leak rate is 30% of the total charge. So once the threshold leak has exceeded or has been exceeded on any system using a regulated refrigerant, the owner must have the system repaired to a point where the leak rate falls below the threshold. If this can't be done, the system must be retrofitted or retired. And this rule applies to systems with a total charge of 50 pounds or more. These leak rate and leak repair requirements are the same for Type 2 and Type 3, so you'll be hearing more about this during next week's webinar. So once it's been determined that an appliance has exceeded the threshold leak rate, the equipment owner or operator has 30 days to repair the appliance so that the leak rate is below the threshold limit. At this time, an initial verification leak test must be performed. Once again, this rule applies to systems with a total refrigerant charge of 50 pounds or more. Under certain conditions and on a case-by-case basis, the EPA can extend this 30-day repair requirement. Although there are a lot of reasons why they will extend, not having a certified technician available to perform the service cannot be used as a reason to extend the appliance leak repair deadline. A system that uses an ozone-depleting refrigerant does not need to be disassembled, removed, or mothballed to extend that leak rate repair deadline. The repair deadline can be extended if the system is temporarily shut down and the refrigerant is recovered from either the entire system or the leaking portion of the system to at least atmospheric pressure. So for example, if an appliance contains 200 pounds or more of a regulated refrigerant, a follow-up verification must be conducted within 10 days. This follow-up verification test is in addition to the initial verification leak test that was performed at the time the repair was performed. So we get this question a lot. So if after repairing a leak, the system fails the initial leak verification test, the technician can make additional leak repairs within that same 30-day window. If repairs are not possible, then a system retrofit or replacement plan must be developed. If the annual leak rate on a system containing more than 50 pounds of regulated refrigerant continues to be in violation, even after repair attempts have been made, the system must be either retrofitted or retired. The retrofitting or retirement process must be completed within 12 months. And during this 12-month period, this leaking system can remain in operation. If this leaking system is going to be replaced with one that uses an exempt refrigerant, the equipment owner has 18 months to retire that system. If a system's annual leak rate exceeds 125% of the total refrigerant charge, a repair, retrofit, retire, or replacement plan must be submitted to the EPA. We get questions about this rule all the time. And yes, a system can have an annual leak rate that exceeds its total charge. And this happens when the system is recharged or topped off multiple times throughout the year. And it's strongly recommended that this be made perfectly clear to your students to avoid any confusion. Like I said, we do get a lot of instructors that seem to be confused about a leak rate of 125%. So if our fellow instructors are confused with that, I can guarantee you that a lot of our students are as well. So this chart that you're looking at right now summarizes the repair regulations that we've just discussed. Again, it's important to note and point out to your students that the leak repair requirements are the same for type 2 and for type 3. The initial leak verification test must be performed before any additional refrigerant is added to the system and before it's put back into service. The follow-up leak verification test is performed once the system has been put back into operation. The guidelines for commercial refrigeration and industrial process refrigeration systems are broken down into two ranges. Those are shown by the yellow and the green sections on the chart, and these are based on the total refrigerant charge. One section from 50 to 500 pounds of charge, and the other range addresses systems that contain more than 500 pounds of refrigerant. For commercial refrigeration and IPR systems that contain between 50 and 500 pounds of refrigerant, a follow-up leak inspection must be conducted once per calendar year to show that the system no longer violates the leak rate limit. For commercial refrigeration and IPR systems that contain more than 500 pounds of refrigerant, follow-up leak inspections must be conducted every 3 months, once a quarter, for 1 year, to show that the system no longer violates the leak rate limit. This is an extremely important chart that contains a great deal of new information that your students must be aware of. As we just mentioned in our discussion of the chart, commercial refrigeration and IPR systems that contain more than 500 pounds of refrigerant, follow-up leak inspections must be every 3 months for 1 year. That amounts to 4 follow-up leak verification tests in addition to the initial leak test that was performed when the system was first repaired. So for these systems, there'll be a minimum of 5 leak tests performed. Another important change to the EPA regulations involves record keeping. All leak inspection records must be kept on file for a minimum of 3 years. And it's the owner and/or operator of the equipment who's responsible for keeping these records. These records include initial leak verification tests as well as follow-up verification tests. And one of the reasons for the owner-operator having to keep these records is there might be more than one company servicing the equipment. So if the service company is responsible for maintaining these records, they will only know and have records of the work they performed. So their leak test or their leak rate calculations might not be accurate if they're not taking into account refrigerant that was added to the system by other contractors. So we'll now shift our attention to leak detection. Not a lot has changed on the leak detection front, but for the sake of completeness, we'll cover some of that information here. So after assembly and installation of a split system, the unit should first be pressurized with an inert gas, such as dry nitrogen and leak check. It's important to note that the nitrogen that we get from welding supply houses is not dry nitrogen. There's typically a great deal of moisture contained in these tanks. Dry nitrogen is a medical grade inert gas and should be used to ensure that the system remains moisture free. And if you want to do a quick test, once you get a nitrogen tank, and I'm talking about a small tank, not the big A tanks, flip the tank upside down and crack open the valve, and you'll see all the water shooting out. So yeah, so this the nitrogen that we typically use in our classes is definitely not dry and contains a decent amount of water. When necessary, a trace amount of the system's design refrigerant can be added to the dry nitrogen to aid in the leak detection process. Adding this trace gas allows the technician to use an electronic leak detector on the system, but again, the leak detector must be capable of picking up the refrigerant that's been added as the trace. So the trace gas will be the same as the system refrigerant. So for example, an R407C can be leak checked with pressurized dry nitrogen and a trace amount of R407C. There has been some confusion over the years regarding the use of a trace gas. It was thought by many that the only refrigerant that could be used as a trace gas is R22, but that's simply not true. The EPA never specified specific refrigerants that can or cannot be used as a trace. Two of the most valuable leak detection methods are your eyes and your ears, and make sure you let your students know about that. When inspecting an operating system that's known to be leaking, they definitely want to look for traces of oil. Make certain that you emphasize to your students that oil travels through the system along with the refrigerant. So when the refrigerant leaks from a system, so does some oil. Although the refrigerant vaporizes, the oil doesn't. It remains behind and can often be spotted. In addition, listening for leaks will help you locate large system leaks. For example, the rotating shaft seal on an open or belt-driven compressor tends to leak if the compressor has not been used for an extended period of time. So traces of oil on this seal indicate that a refrigerant leak is likely. Of course, soap bubbles are a very efficient way to pinpoint leaks, and as instructors, we all know that this method is the least expensive and making it a really popular choice for use in our training program. On systems equipped with capillary tubes or fixed bore metering devices, superheat calculations are used to determine if an evaporator is operated with an excess or deficiency of refrigerant. Excessive evaporator superheat in a cap tube system is an indication of a leak. Be sure to provide your students with some examples of superheat calculations as well as some other causes for high evaporator superheat. Because as we know, a refrigerant leak is not the only cause for high evaporator superheat. Well, we'll now move on to some recovery content as it applies to Type 2 appliances. Previous regulations required that companies that service Type 2 appliances must own and register active recycling and recovery equipment. Although these companies are still required to own and, of course, use active recycling and recovery equipment, the companies are no longer required to register these units with the EPA. Before refrigerant recovery from a system, be sure to determine the maximum amount of refrigerant that's contained in the system. If the refrigerant charge is greater than 15 pounds, system-dependent or passive recovery techniques cannot be used. This is because the EPA prohibits the use of these recovery methods on appliances that contain more than 15 pounds of refrigerant. So if the system contains more than 15 pounds, then technicians are going to need to use active recovery equipment to perform the recovery process. Make certain that your students know how to properly prepare and set a system up for a refrigerant recovery process. Before recovery, always check the service valve positions, check the recovery unit's oil level, evacuate and recover any remaining refrigerant from the unit's receiver. Now, I just want to just bring up one term. We recover refrigerant, we evacuate a system. Some of the EPA terminology talks about evacuating refrigerant. And it's not a term that we typically use. Like I said, we recover refrigerant and we perform evacuation processes on equipment. So we recover refrigerant, we evacuate systems. The EPA does state that we evacuate refrigerant, and that is the EPA regs as written, so we're not allowed to change that. So you might definitely want to alert your students if they see a question on the EPA test that talks about evacuating refrigerant, and what they're actually talking about is recovery. Always alert your students that recovered refrigerant may contain impurities such as acids, moisture, and oil. So instruct your students that if they smell a sharp, pungent odor while gauging up on a system in preparation to recover refrigerant, they should alert you immediately. Sharp, pungent odors are an indication that a compressor burnout has occurred. If the system has indeed experienced a compressor burnout, an oil sample should be taken so that can be tested for the presence of acid. It's important that you also stress, both in the classroom and in your labs, that refrigerant hoses are required to have low loss fittings on them. These fittings can be self-sealing or manually manipulated. And it's always a good idea to make sure that your students know how to use them. Another note on recovery: before transferring refrigerant to an empty DOT-approved refrigeration or recovery cylinder, make certain that your students evacuate the cylinder to reduce its pressure and remove non-condensables. Otherwise, good refrigerant can become contaminated if it's transferred into a recovery cylinder that has not been properly evacuated. So it's super, super important that we stress that with our students to avoid contaminating good refrigerant. Before recovering refrigerant from a parallel pipe compressor system or rack system, we need to make certain that the equalization connections between the compressors are closed. If these equalization lines are left open, the recovery process time will be affected. In addition, and probably more important than that, if these equalizer line connections remain open, oil can be pulled from one compressor to another, putting other system compressors in danger of experiencing mechanical failure due to lack of lubrication. So it's important that these external equalizer lines be shut. One phrase that your students are going to see as they prepare for this exam is that water-cooled condensers are generally connected to the local municipal water supply. And local municipal water supply is a term used by the EPA in the regs, but you should definitely let your students know that local municipal water supply simply means tap water. Since liquid refrigerant is more dense than vapor, liquid recovery is faster than vapor recovery. So liquid recovery is initiated by connecting the service hose to the system's liquid line. To remove the most liquid refrigerant from a system, the service hose should be connected to the lowest part of the system known to contain liquid. For example, if the condenser outlet is located below the receiver, it's best to recover liquid refrigerant from the outlet of the condenser. So we want to recover from the lowest point known to contain liquid. It's also important that you let your students know that once all of the liquid has been recovered, they're not done, as the system still contains vapor refrigerant. This vapor refrigerant must also be recovered. On larger systems, the amount of vapor refrigerant left in the system can be pretty significant. Although liquid recovery might be faster, there are times when a slower option is desirable. Recovering refrigerant in the vapor phase, although slower than liquid recovery, will minimize oil loss from the appliance. This is important, for example, when the system repair does not involve compressor replacement. Remind your students that when a compressor is replaced, the new compressor comes with a full charge of oil. So a loss of oil during liquid recovery will have no negative effect on future system operation. This, however, is not the case when the system compressor is not being replaced. After recovery, refrigerant may be returned to the appliance from which it was removed, or to another appliance owned by the same person without being recycled or reclaimed. Remember, old reg, new reg, saying refrigerant cannot change ownership that's been recovered. Also, make certain that your students know that although recovered refrigerant can be reused, this is assuming that the recovered refrigerant was stored in a recovery cylinder that was properly evacuated prior to the recovery process. Once again, if the recovery tank was not properly evacuated, there's a good chance that that recovered refrigerant is now contaminated. If refrigerant is being recovered from a system that's being disposed of, it's important that all HVAC service companies keep records for the system for at least 3 years. And this regulation applies to each system appliance that has a refrigerant charge between 5 and 50 pounds. This next slide basically talks about high pressure going to low pressure. If we increase the pressure differential, we're going to increase the rate of flow from high pressure to low pressure. So the refrigerant recovery process can be sped up by increasing the pressure difference between the system and the recovery tank. And this can be accomplished in 2 ways. First, the recovery cylinder can be cooled to lower its pressure. Second, heat can be added to the system to increase the pressure in the system. Either method can be used to increase the pressure difference between the system and the recovery cylinder. During the recovery process, closely monitor the temperature of the recovery unit's compressor. This is because the hermetic compressor motors on recycling and recovery units rely on the flow of refrigerant to cool them. Because of this, the motors may overheat, especially when the system pulls into a deep vacuum. In addition to the hermetic compressor overheating during the recovery process, the windings of a hermetic refrigeration compressor could become damaged if energized while in a deep vacuum. So exercise caution to prevent this from occurring. This chart outlines the required levels of evacuation during recovery for type 2 appliances. Just as a reminder, although this was covered in earlier webinars, the pressure classification is now based on the refrigerant's liquid phase pressure at 104 degrees Fahrenheit. If you look at the pressure temperature chart that's supplied with the EPA prep manual, we highlighted the 104 degree line to make that more evident. So very high pressure refrigerants, such as R744, which is carbon dioxide, will have liquid phase pressures over 340 psig at a saturation temperature of 104 degrees Fahrenheit. High pressure refrigerants, such as R22, R410A, R407C, and R422B, have liquid phase pressures between 155 and 340 psig at that 104 degree Fahrenheit saturation temp. Medium pressure refrigerants such as R12, R600A, R409A, and R1234YF have liquid phase pressures between 30 and 155 psig, once again at that 104 degree Fahrenheit saturation temp. So be sure to provide your students with examples that require the use of this chart, as they will need to know this information to take and successfully pass the exam. All bets are off with regards to that chart we just looked at if the system's leaking. If the system is leaking and the prescribed vacuum levels can't be reached, the system refrigerant only needs to be recovered until the system's internal pressure reaches atmospheric pressure. On the refrigeration cycle and accessory front, make certain that your students are well aware of system component locations in the system, especially the refrigerant receiver, as this is an important component with regards to refrigerant handling. Of course, you'll only find refrigerant receivers on systems that are equipped with modulating metering devices, such as thermostatic expansion valves. Since the receiver is located at the outlet of the condenser, the state of the refrigerant at the inlet and outlet of the receiver is, on a properly operating system, a high pressure, high temperature, subcooled liquid. If the system being serviced has a refrigerant receiver, the system should be pumped down so the refrigerant is stored in the receiver and condenser coil whenever possible. Be sure to explain this to your students so they'll understand the process of system pump down as well as when it can and can't be done. And this will depend on system configuration and also the repairs being made to the system. Some systems are equipped with moisture indicating sight glasses. These moisture indicators are located downstream or immediately after the liquid line filter dryer. When the moisture indicator, which is typically a colored dot, changes color, often from green to yellow, the system contains excessive moisture. In this case, the moisture issue must be addressed and the filter dryer must be replaced. Stress to your students that anytime the system is open for service, the filter dryer should be replaced. If ice forms on that moisture indicator glass, an alcohol spray can be used to remove it. Be sure to tell your students never use sharp objects to scrape or chip ice from the glass on these moisture indicators. Ice on a sight glass is one indication that the filter dryer is clogged. So remember, since the filter dryer and sight glass are installed in the liquid line, there really should never be frost or ice on the liquid line or its components. If there is frost forming on the sight glass, that's an indication that the filter dryer might be clogged. In addition to the high side system components such as filter dryers, sight glasses, and receivers, your students will also need to know about low side system accessories such as the accumulator. The suction line accumulator is located at the outlet of the evaporator, and it prevents liquid refrigerant from flowing into the compressor. One thing I really like to do in class, when I'm discussing the accumulator with my students, I reference the refrigerant receiver in the same discussion. The accumulator is on the low pressure gas line, while the receiver is on the high pressure liquid line. The receiver is used to ensure that 100% liquid enters the metering device, while the accumulator ensures that 100% vapor enters the compressor. So the accumulator and the receiver are pretty much polar opposites of each other. And I use that analogy there to help the students understand the concepts and how these two components work. Service valves are also classified as system accessories. It's important for your students to know the types of service valves as well as the various positions they can be placed in. We are referring to the positions of back-seated, front-seated, mid-seated, and cracked off the back seat. Stress to your students that the normal operating position of suction or liquid service valves is back-seated, and it's in this back-seated position, and it's only in this back-seated position that the gauge port is closed off so the manifold hose can be removed from the valve without releasing system refrigerant. On semi-hermetic compressors, another service valve can be found, and this is the discharge service valve. As with the suction and liquid service valves, the normal operating position of this valve is back-seated. Under no circumstances should the discharge valve be closed or front-seated on an operating reciprocating compressor. Front-seating this valve can result in major compressor damage as well as severe personal injury. It's important that your students are aware of the dangers associated with improper valve positioning. You also need to let them know that if they have any doubt, they should ask for assistance before energizing the system. To help prevent compressor damage, the refrigerant systems must be protected by a high pressure relief device. When a system is protected by multiple pressure relief valves, they're to be installed in parallel with each other. Pressure relief valves are never to be installed in series with each other. If we install them in series, what's going to happen is if the pressure builds up, that first valve is going to open, but now that's going to feed to the second valve, and that second valve is then going to have to open. So that's going to delay the response time or delay the relieving of pressure from the system. So relief valves are intended to protect the system from unsafe operating conditions. Another accessory that's used to help protect the system components from damage, namely the compressor, is the crankcase heater. So crankcase heaters are used on the system to reduce the amount of refrigerant in the oil and reduce oil foaming, which can occur in the compressor crankcase. Refrigerant-laden oil is typically present in the crankcase when ambient temperature is low and the compressor is not operating. If oil foaming occurs, the lubricating capability of the oil can be greatly reduced. This can cause severe internal damage to the compressor. So in your teachings, it's important to let your students know that those crankcase heaters should be energized at least 24 hours prior to turning the system on. Just a couple of quick words about system evacuation. It's important that your students know how to measure deep vacuums and know how to use the instrumentation, namely a micron gauge, to do so. So that magic number, that vacuum level 500 microns, needs to be achieved to ensure that all the moisture and non-condensables have been removed from the system. Common non-condensables are air and nitrogen. If non-condensables remain in the system when it's charged and put into operation, the discharge pressure will be higher than desired and the system will not function as intended. On the chiller side, when charging a chilled water system that's in a deep vacuum, it's important to start charging the system with vapor refrigerant. If we charge liquid into a system that's in a deep vacuum, that liquid can flash to a vapor and that can cause any non-moving water in the chiller barrel to freeze. So it's recommended that vapor refrigerant be added to the system until the temperature that corresponds to the system pressure is above 32 degrees Fahrenheit, preferably in the 36-degree range. So for example, if an R410A chiller is in a deep vacuum and we need to charge it, vapor refrigerant should be added to that system until the system pressure is approximately 110 degrees. This pressure corresponds to a temperature of 36 degrees and will prevent the water in the chiller from freezing. Of course, in order to determine the pressure to which a system should be vapor charged, your students will need to know how to read a pressure temperature chart, so be sure to give them lots of practice with that. On the refrigerant safety front, your students definitely need to know about ASHRAE Standard 15. This standard requires that a refrigerant sensor be located in equipment rooms. These sensors will trigger an alarm and automatically start a ventilation system if unsafe concentrations of refrigerant are detected. It's also important to note that some applications, such as equipment rooms that use R717 ammonia, don't require a leak sensor if the room's mechanical ventilation system is continuously operated. And that pretty much sums up type 2. In the brief amount of time remaining, we will now address as many questions as possible.
Eugene, we have one gentleman would like to know why is it taught to place the vacuum gauge as far away from the vacuum pump as possible when pulling a vacuum?
Yeah, that's a really, really good question. So I'll give an analogy with that. Let's say you have a room filled with people, and the room, everybody in that room, they're elbow to elbow, shoulder to shoulder, and the room is jam-packed. And there's a door on one end of the room, and that door opens, and now people start to flow out of the room. They're leaving the room. Well, the people by the door are getting out first, and the concentration of people at that door is lower than the concentration of people at the back of the room that are still elbow to elbow and shoulder to shoulder. So it is possible that if you have a micron gauge close to where the vacuum pump is located, that you're going to get abnormally low or inaccurately low readings, when in essence, there's still a lot of air, nitrogen, non-condensables that are still in the system. So we try and keep the micron gauge as far away from the vacuum pump as possible, because now if we're reading 500 or 400 microns at the far end of that system, the vacuum everywhere else in that system is actually going to be lower than that point? That's a great question.
Yeah, another thing is that on smaller systems, you don't have a place to connect the vacuum valve because you only have processed stubs or what have you. So one thing to remember is once the vacuum is achieved, to let it sit idle, valved off, and wait a few minutes to make sure the whole system is at the same level, because it may take, just like when you add a refrigerant, it takes a while for everything to stabilize. So does the vacuum take a while to stabilize.
We have any more questions?
I'm looking at the moment. We also had a question about EPA saying, some books saying to use R22 as the trace gas.
The EPA, yeah, just to hop on that, the EPA never specifically mentioned R22. The industry, not the EPA, the HVAC industry picked R22 because it was a safer refrigerant, but the EPA never specifically mentioned R22 by name. So it was industry accepted that R22 was the trace gas to use, but that was never stated by the EPA.
Okay, it looks like that's all of our questions. Again, I'd like to thank all of you for attending, and if you come up with any questions, feel free to contact one of us. And as I always say, if we don't know the questions, we'll definitely try to find out, the answers to the questions. We will definitely try to find the answer for you. So on that note, again, thank you for attending.